Hello everyone, my name is Casey McKinley, and I'm going to be walking you through my final project for digital cryptography. My project is called PCAP Explorer, and it is essentially a tool that is designed to visualize communication, visualize trends in communication between IP addresses. So it takes in a PCAP, and it processes that PCAP. It uses TCP flow to carve some files out of the PCAP, and then it opens a web application that visualizes all this data and allows us to explore it in sort of intuitive and interesting ways. So I'm going to walk you through all that today. So to start off, let's pull up the built-in help menu for my application. So you just do Python PCAP Explorer.py-h. So here you have it. So PCAP Explorer, a Python utility for the digital forensics investigator, ingests a PCAP, aggregates communication statistics for IP pairs, and launches a web-based visualization. So it has a bunch of different options. At least one of the following options, -I and -s, at least one of them has to be specified. -I specifies the PCAP file to ingest and process, and -s launches a server to actually spawn the web app. To serve up the web app. So the reason we have all these options is there's a lot of pre-processing involved in ingesting that PCAP and spitting out the data in the appropriate format. So I set up the arguments in such a way that you could do it all in one shot, where you ingest and immediately launch the web app, or if you've pre-processed the data previously, you can just go straight to launching the web app. Or if you don't want to launch the web app right now, you can just process the data. So the most common command that people will be issuing would be something like this. So -A essentially combines the -T, -S, and -B flags. -T enables the TCP flow integration, which carves the files from the TCP sessions in the PCAP. The -S flag spawns a Python web server, so we can actually visit our application on the local host. And then -B actually sends a request to your default browser to open localhost at whatever port you specify, or if you don't specify one, at 8000. So yeah, again, so there's -P that allows you to specify a port. There's -O that lets you specify a specific out file. Note that the default out file is data.json, and that is the actual very specific file that the web app looks for. So while you can write out to other files, it's not going to help you in terms of the web app if you do. -I specifies the in file, and -H brings you to this menu. So as I mentioned, the pre-processing of my application, of the actual Python portion of this, can take some time. So I've gone ahead and done the pre-processing before this tutorial, just for the purposes of expediency. So I'm going to open what I already have. So here's what you would have seen if we had gone through the process of processing the PCAP before launching the web app. So it tells you what's going on, starts by parsing the PCAP, it removes some old files in the directory of TCP out. That's where the TCP flow stuff is stored. Now it actually runs TCP flow, carves the files, we process the TCP flow output, and we write all the data, all the statistics that we've aggregated into data.json. Now this took about 4 minutes in real life, so it wasn't really worth showing you that in the video. Again, but this is just pre-processing time, so you wouldn't necessarily have to wait this long every time you want to view the data, because once you have the data.json file generated, you can just go ahead and launch the web app as I'm about to show you. So to launch just the web app after the data has already been generated, you can do PCAP Explorer -B-S. So B is for browser. It's actually going to open our browser for us, and -S is what's going to launch the Python web server. So here we go. So when it first opens up, it might appear like this. That's because the page, when it renders, determines how big the graph should be. So if the page, if the graph decides to render when the window is expanding, it'll sort of make itself short and stout like that. So if we just refresh, it should get some correct dimensions. See, so there we go. Now this isn't very interesting at first. We're looking at a pretty boring IP, it looks like, but let's explain the layout a little bit here. So up here is the name of the file that you parse. Over here, we have a drop-down that lets you select other IPs. Actually, I'll get back to that in a second. Over here is what kind of tells you the context of what we're looking at. So we see this IP address right here. So all the data on the current view is in the context of this IP right here. So the IPs on the y-axis, actually, you know what, let's switch to a more interesting one, and I'll explain these views to you in a second. But so the IP, so you have this IP here, so that's 192.168.15.4, and he's the main IP. Everything in this view is in the context of him. These IPs on the y-axis here are IPs that this guy has communicated with, and the protocols on the x-axis here are the protocols that 192.168.15.4 communicated with these other IPs. So if we hover over this over here, this tells us that 192.168.15.4 sent 6 messages to 12.129.147.65 over the HTTP protocol and received 6 also HTTP messages from the same 12.129.147.65. And here we see that 192.168.15.4 sent 0 messages to 12.130 and received 7 messages. And again, this is the data text lines protocol. So when we capture these protocols, obviously there's a whole stack of protocols in a given packet. When we're parsing, when my script parses the PCAPs, it just grabs the highest layer protocol. So it'll be either transport layer, TCP UDP, or application layer, like HTTP or SSL. So in any event, you'll also see that we have some color coding going on. So these nodes that are at the intersection of these lines are encoded by the amount of traffic that they have communicated with the main IP is encoded by the size of the node. And the color indicates whether it was sent or received. So a green node indicates received. So 192.168.15.4 received 7 messages from 12.130. And then a red node indicates sent. So he sent 5 messages to 128.241, etc. over the HTTP protocol. And where we have these kind of overlaps, that's because there's sending and receiving going on between these two IPs over this given protocol. So that's sort of the explanation of this. This down at the bottom here is a little legend, so it tells you that the largest node on the screen is 76, so that would be this guy, and the smallest node is 2. It's to sort of give you a sense of scale when you're trying to appreciate how big one node is compared to another in terms of a numeric value. Now this statistic here shows that our main IP 192.168 sent a total of 34,000 packets and received a total of some odd 39,000 packets. Now this bar over here shows all of the is just a list form of all of these guys on the y-axis here, and you'll see that the corresponding y-axis element highlights when we scroll over the one in the list. And same thing when you scroll over a node that corresponds to that specific y-axis. Now these figures here indicate, so this sent 24, received 36, indicates that in aggregate over all protocols, 12.129.147.65 sent 24 packets to 192.168.15.4 and received 36 from him. And again, this is an aggregate. These nodes are all on a per protocol basis. So now this is all well and good, but you'll notice up here too that we have some paging going on. So this is because if we implement paging when The main sort of focused IP, so that's 192.168, spoke to too many people, and the y-axis would just be too crowded if we included all of them. So we implement paging so that we can scroll through groups of other IPs. So now if we hit next, you'll see that the nodes sort of switch around and the y-axis gets loaded with new IPs. And again, but our context has stayed the same. It's still 192.168.15.4. These are still all just people that he has communicated with. And again, similar layout. And we can see that as we continue to go, and we can go backwards. And again, this is just showing us different levels of communication. Now we can switch to different contexts, so different focuses. So right now it's in the focus of 192.168.15.4. We can switch to a different person, or a different IP rather, by one method is to go to this drop-down box and select an IP address from this drop-down. And so this guy is kind of boring. He only communicated with one person, and it looks like he only sent one packet. So not really a whole lot of interesting stuff going on here. So in that case, we want to kind of look for the most interesting ones. So I've implemented a sort of overview system where you can look at some big aggregate statistics for all of the different IPs in the packet capture. So this first column is the total number sent by the given IP. The total number received, the total traffic volume, such as the combination of these two values, and then the total number of parties that the given IP is communicated with. So this is probably the most interesting value. The ones who communicate with the most people would also likely have the most traffic, and also probably have the most varied traffic. And so the two here are these two, so that's 192.168.15.4, which we've already looked at, and 192.168.1.64. Again, we can look at any of these and we can click on them, and it does another context switch. Now we're looking at the data for 209.73.191.242. But again, let's go back to one of the more interesting ones. So now also another way you can switch between users is by right-clicking one of these entities. So if you right-click somewhere on the list, it'll switch to that person. Or if you right-click on a node, it'll switch to that person. And that, again, just allows us to switch views fairly easily. Now, suppose you wanted to increase the number of IPs you see on a single page, so you get a broader overview. It might crowd your screen, but depending on how big your monitor is, that might be okay. So I've implemented this configure screen, which allows us to determine how many IPs actually get displayed per page. And so let's up this guy to 20. And so now it's still the same IP, it's 192.168.15.4, but now we're looking at 20 IPs per page as opposed to, just 10. And that can be scaled as far as 100, I think, but I have a feeling that would be a little crowded. Now, the most informative feature that I haven't really talked about yet is the summary overlay that pops up. So if we click on an entry here or on a node in here, we get some more detailed information. So now this is a summary for all of the statistical data about the traffic exchange between 192.168.15.4 and 168.143.188.82. So this shows that 192 sent 244 packets to 168 total across all protocols, and that 168 sent 340 total to 192 across all protocols, and they exchanged 584 packets total. Then we can do a little more fine-grained and look at specific protocols, and I've also included the percentages of how much of what these protocols make up in terms of the total traffic. So HTTP represents 6.85% of the total traffic exchanged between 192 and 168. TCP represents 86% of it, so it totally overshadows it. And again, here we have similar statistics to the aggregate traffic up here, just on a per protocol basis. And now if you scroll down below, if you'll remember, TCP flow is integrated into my Python script. So when we process the data, we calculate all these statistics that I've been showing you with the packets sent and received per protocol and in an aggregate. But we also take note of all the file names that correspond to a given IP address as output by TCP flow. And then we bundle that all up into our data.json, and we allow us to look at it in here. And now the benefit of this is that we actually have an interactive display now, and as you'll see, image files that are parsed out by TCP flow get displayed inline, but we can also click on things. So like this is an HTML file, so we can click on that and see. So looks like it's obviously not a complete file, but you know, an investigator can go through and they can investigate source and they can just kind of click through things pretty easily, all while staying inside of this web application. And they can just continue to explore like that. And again, you can switch between lots of different views, and you know, you could configure this to be some crazy number. So let's try 70. It'll probably stop being readable. But yeah, so it can display lots of data in a very condensed format, and the hope is, with any sort of information visualization project, is that humans are very visual learners, and that by looking at visual encodings of numeric information, they might more quickly be able to draw certain conclusions and grasp certain trends in the data that you wouldn't necessarily be able to by just looking at numbers or by looking at a packet capture in Wireshark. And so that about covers it. This is about the extent of the application thus far. If you have any questions, feel free to reach out to me at cmm771.nyu.edu. And thanks for listening. So long.